Welcome back. So as we continue discussing how the electrons in the atoms relate to the periodic table, and we talk about the Bohr's theory, and we talk about the quantum theory, as a quick review, remember that the quantum theory tells us that the electrons are going to be arranged around the nucleus in different energy levels. And what we see, the places where they're located, is just a probability of finding them there. So the quantum theory is based in probability. And we can do this like on density maps. So we can have, for example, something say that the electron is going to be found probably like on a circle around the nucleus, and the more dots we have, the higher the probability that we find the electrons there. We also have to recognize that this is a 3D, so that's not going to be like a circle per se. It's going to be more like a sphere. So imagine that being like a 3D. So the electron is somewhere on that place in there, and we're going to call that type of probability shape, we're going to call that one the s orbital. And we also say that the maximum number of electrons on an orbital is 2 electrons. We have another type of probability that looks like this, and we're going to call these the p orbitals. But since we're talking on a 3D space, it could be like that. There's going to be another one that is like that, and another one that comes toward you and goes behind the plane or the screen in this case. And we're going to call this the P on the x-axis, the P on the y-axis, and the P on the z-axis. So altogether, each orbital can have a maximum of 2 electrons. So the p orbital is going to be equivalent to 6 electrons. When we talk about the d, and I'm not going to draw the d, that's going to be equivalent to 10 electrons because there are 5 of them. And the f is going to be equivalent to 14 electrons maximum. So 2 on each orbital, there's 7f, 5d, 3 p's, and 1 s. And all that is the possibility of finding the electron there. So every time I'm trying to talk about the electrons, I'm trying to describe the electron to somebody else to communicate. I cannot afford to be doing these drawings all the time. So I'm going to have to come up with a new way of communicating that information without having to be drawing all the time. So we call that the electron configurations. So the electron configuration is a system that we have designed to tell you where the electrons are without having to do drawings all the time. And it's going to depend on the labels that we're giving the electrons, or the orbitals, sorry. So the labels of the orbitals, which are going to be S, P, D, and F, knowing that this one can accommodate a maximum of 2 electrons, a maximum of 6 electrons, a maximum of 10 electrons, and a maximum of 14 electrons. So with that, we can describe any element in the periodic table in terms of in terms of where the electrons are located. And it's also important to know that we have a 1s orbital versus the 2s orbital versus the 3s orbital. Then those are the ones that are going to look like this. It's going to be like a sphere inside another sphere. So let's see how we're going to do this. So one thing we have is a lot of information that has been found on the lab by doing experiments. And we know, today, based on the quantum theory, we know how the electrons begin to accommodate themselves to the nucleus. Since the electrons are negative and the nucleus is positive, the electrons want to be as close as possible to the nucleus. However, If you have a lot of electrons, not all of them can be as close as possible to the nucleus. So they're going to have to start spreading. And the way they spread is given by this order. The first two electrons are going to be on the 1s, obviously, on number 1, followed by the number 2. But then the number 2 is going to divide into s and p. Then that's the maximum you can put on number 2 because it's still close to the nucleus, so it's kind of small. Then you go into number 3, which is farther away, so bigger space. And you can put the 3s, the 3p. And then we see that we have the 4s followed by the 3d. And you're going to say, wow, there's a jump in there. How come the 4s is being filled before the 3d? And the reason is, if we go back to the Bohr's model, you have the nucleus, and then you have level 1, level 2, level 3, level 4. So the farther you get away from the nucleus, the closer and closer they begin to be to each other, and they start overlapping. So it's a lot more complicated than that. So for our purpose, just use what the scientists have already designed and follow the order that is given. 1s, followed by 2s, followed by 2p, followed by 3p, followed by 3p like a 3s, 3p. Then the 4s comes first, then the 3d, the 4p, the 5s. So you can see that there's between the s and the next one is a overlap in there. So do not try to memorize that. On your test, you will have this diagram available to use. So it's another tool you get to use. You can have it like that, or you can have it like this. I like this one better. I like this one better because this one tells you we're always going to begin with the lowest energy. So we're going to fill up the 1s. Then we're going to fill up the 2s. Then we're going to go, as we go up into the energy, then we're going to go into the 2. But there's going to be, that's where we find the p. And we know the p have a maximum of 6 electrons. We know the maximum number of electrons per orbital is 2. So there going to be 3 of them. And all of them are the same energy. So you got 1 here, 1 there, 1 there. So this is better than this, where it doesn't show you that. So I prefer to use the orbital diagram for the order because it tells me, hey, remember, you have 3 p's. Remember, you always have 3 p's. When you make it to the D, remember, there's going to be 5 of them. And we're going to see how we're going to fill that up, following some specific rule that we're going to discuss, like the Pauli's principle and the Hund's rule. So let's see how we're going to do that. So I'm going to, like I told you before, I prefer to use this one to fill up, to distribute my electrons, because it shows me how the p's and the d's break into 3 and 5. So let's do this problem. We want to write the full electron configuration for each element. So according to this, we're going to write first the 1s. Then we're going to follow with the 2s. Then we're going to follow with the p's, 2 p's. Then we're going to follow with the, as we go up the scale, with the 3s. And I can continue writing, but based on the element, I do not need all of them. So let's see how many we need. So I'm doing strontium. And according to the periodic table, strontium is number 38. So that's the atomic number, which means I have 38 electrons. So what it's telling me, I have to put a total of 38 electrons in here. So on the S, maximum 2. On the X, maximum 2. And notice I put the number on top. On the P, maximum 6. I got 10 so far. So that would be 12. So that means I need to continue writing. So then I'm going to have my P's, 3 4p with a maximum of 6. Then I'm gonna go into my 4s and then my 3ds. So 4s and 3d. So let's continue counting now. So far I have 2, 4, 10, 12, 18, 20, 30. So I need 8 more. So the next one is the 4p, which I'm gonna put 6 in there because that's a p. And then my last two are gonna be my 5s2. And that should be 38, so let's check. 2, 4, 10, 12, 18, 20, 30, 36, and 38. And that will be for strontium. But I want you to notice something very important here. So this is number 1, number 2, number 3, number 4, back to 3, number 4, and number 5. So the last one, the highest number, is gonna be 5s2. And this is important because look at this. Remember, 5s2. Look at this here. I'm doing a strontium, and this is period 1, period 2, period 3, period 4, period 5. Remember, the last number was 5s2. And this is group number 2. So period 5, number 5. Group 2, number 2. So the quantum theory, when we do the electron configuration, matches exactly with the periodic table. And this, to me, is so amazing because the quantum theory was developed around the mid-20th century. The periodic table was developed earlier to the end of the 19th century, earlier the 20th century. So a theory that was developed like 50 years later confirmed the way we organize the periodic table. So that's amazing, the way everything matched. So it's a very strong theory when you come up with something new 50 years later and it still holds. So that's how we do the electron configuration for strontium. Let's go ahead and do germanium. So for germanium is going to be number 32. So that means we're going to have 1s2, 2s2, 2p6. That's 10 of them so far. We need 32. 3s2, 3p6, 4s2. That's 10 more. So we need 12 more. 3d10. So 3d10, 4p, how many do we need? We got 20, 30, 4p2. So let's check. 20, 20, 32. So that tells me that I should find germanium in period 4, group 14. How do I know that? Let's see, germanium. Period 4, group 14. So germanium is going to be located right there, which is period 4, group 14. How did I know it was going to be group 14? Because my last two numbers was P, and there was two of them. And I'm going to show you very soon that this is what we call the P block, and that's going to be 1 electron, 2 electrons. So I'm going to talk about that later on detail. So let's go ahead and do another one. Let's go ahead and do lithium. Lithium is atomic number 3, so 3 electrons. So 1s2, 2s1. So that's 3 electrons, which tells me lithium is going to be on period number 2, 1 and 2. And it's going to be 1 electron on the S. So this is what we're going to know very soon as the S group. And lithium is 1 on the 1 electron column. And then we have krypton. And krypton is going to be number 36. So that's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. We're going for 36. So let's see how many we have so far. Got 10 in there, 10 more in there, 10 in there. So we need 4p6. So we need 6 more, which tells me krypton is going to be on period 4 because that's the highest number. And it's going to be on the block P, it's going to be number 6. So let's see. So this is group 1, period 1, period 2, period 3, period 4. So do we find krypton on period 4? Yes, we do. And I told you that this is the P group, 1 electron, 2 electrons, 3 electrons, 4 electrons, 5 electrons, 6 electrons. So this matches perfectly. So the highest one is going to be period 4 with a total of 6 electrons on the P block. So let me tell you more about those blocks. So we know from experimentations and all that the way the periodic table is going to feel is going to be like this. This is going to be my S block. This is going to be my D block. I'm sorry. Helium is kind of special. So this is going to be my P block, and this one here is going to be my F block. So what that means is any of these elements in here, they always going to end with a p orbital. Any of these elements in here, they're always going to end on the highest number on d orbitals, and so on and so on. So when you do the daily work, double check that. Let's see if when you get the electronic configuration, look at the highest number and look at the letter with that highest number and see if it falls in one of those blocks where the electron is, where the element is. So go ahead and work on these 4 problems. And now we're going to do something different. Now we're gonna fill up the orbitals. So we use the orbital diagram for the order where I needed to fill it. So I knew I had to do the 1s first, followed by 2s, followed by the 2p, followed by the 3s, followed by the 3p, followed by the 4s, followed by the 3ds, followed by the 4ps, and so on. So that gave me the order that I needed. However, I now want to show you more information. So what I'm gonna do, I'm gonna use the orbital diagram to fill up. Instead of writing my electron configuration, I'm gonna fill it up. So for example, let's do oxygen. So oxygen, which is right here, is gonna have an atomic number of 8, so 8 electrons. So with 8 electrons, all I have to do is fill up my orbitals. Remember, maximum of 2 electrons per orbital. So I'm gonna represent my electrons with something like that, with a semi-arrow. So I'm gonna put 1 electron there, and I'm gonna put another electron there. But if I do it like that, that's wrong, because the quantum theory tells me that if I have 2 electrons on the same orbital, one of them has to be rotating on its own axis clockwise, while the other one is rotating counterclockwise. So we don't go as deep as to be able to explain why on this course. Just be aware that we call this the Pauli's principle, which tells us if you have 2 electrons in the same orbital, one of them has to be spinning one way, the other has to be spinning on the opposite way. And we represent that by putting one pointing up and one pointing down. So 2 electrons on the same orbital have to be spinning on opposite ways. That's the Pauli's principle. So we're doing oxygen with 8 electrons. So far we have 2. Then we go to 2s, and we follow the Pauli's principle. So that's 4. Then the next one is 2p. And if I do that, I will get it wrong, because there's another rule that tells me. So you already understand the Pauli's principle. There's another rule that tells me if you have more than one orbital at the same energy, do not put 2 electrons together. Electrons are negative. They do not like to be together. So if you have orbitals with the same energy, do not force them to be together. You just put one by itself. You still have the same energy. You put another one. So far we have 4, 6, and you put another one. Now that you have put the electrons on the same energy individually, if you need to put more, then now you have to force them to be together. But remember to do the Pauli's principle, which tells you that they have to have opposite spins. So, but before we finish that, the fact that you have to put them separate, that's what we call the Hund's rule. So the Hund's rules tell us that if you have orbitals on the same level, number 2, number 2, number 2, with the same energy, do not put 2 electrons together. Fill up those individually first, and then if you need more, like in our case, then you put it together. So Pauli's principle, 2 electrons on the same orbital, opposite spins. So we represent that with one pointing up, one pointing down. Hund's rule, if you have more than one orbital at the same energy, do not put 2 electrons together unless you run out of space. So before you jump into level 3 on this case, make sure that you fill up whatever you have left. So applying the Pauli's principle and the Hund's rule, we come up with this orbital diagram for oxygen. which is nothing more than on the 1s, I have 2 electrons. On the 2s, I have 2 electrons. On the 2p, I have 4 electrons. So as you notice, the highest number is number 2. So we're going to find oxygen on period 2. And on period 2, you have a total of 6 electrons. So we should find oxygen on the P. We should find it on the group number 4. So let's find out. So is that the case? So I said period 2 and on number 4 for the P. So period 1, period 2. So that's where I find oxygen. And this is my P group, and it's going to be on 1, 2, 3, and 4. And that matches with that. So let's do another one. Let's do chlorine. Chlorine have 17 electrons, atomic number 17, so 17 electrons. So 1 and 2, Pauli's principle, opposite spins. That's 4, 5, 6, 7, following Hund's rules. And then I had to force it 8, 9, and 10, 11 and 12, 13, 14, 15, 16, and 17. So the highest number is going to be 3, and all together we're going to have 5 electrons on P. So the highest number is 3. So 1, 2, and 3. Do we find chlorine on that one? Yes, we do. On the P, do we find it on number 5? 1, 2, 3, 4, and 5? Yes, we do. So that tells us exactly where we're going to find it. Let's do another one. Let's do silver. Silver is going to be atomic number 47. So let's do 47 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. Oops, sorry. I jumped one. Let's go again. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47. So this tells me what is my highest number. My highest number is not 4. My highest number is 5. However, transition metals, you're going to have to be careful because you're going to have to look at the last one that we filled. And it's telling me that on D, I'm going to have 9 electrons. So let's see, on my D block, which is this block here, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And that's where we find silver on period 1, 2, 3, 4, and 5. So the highest number gives me the period, and the last one that I fill tells me where the on what group is going to be located. And let's do one more, and then you get to do it on your own. Let's do cadmium. Cadmium is going to be 48. So it's basically the same thing we did with silver, but with one more. So 1, 2. So we're gonna fill one more, which tells me, so all this is gonna be filled up like this. So I'm just basically repeating the same thing I did with silver, but I just added one more electron. So that tells me the highest number is going to be 5, which is what I know. 1, 2, 3, 4, 5. So cadmium is right there. And the highest letter I'm going to fill up is the D with 10 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And that's where I find cadmium. So everything matches. So this is a different way of showing how the electrons are distributed, not by writing the electron configuration, but by drawing the electron orbital diagram, which allows me to see the way the electrons are spinning, opposite spins, and how do they fill up. Because it's going to be very important very soon to understand how many electrons, like when you look at here, every single electron is paired. So on this particular element, all the electrons are going to be paired. If we were doing fluorine, for example, fluorine is going to be atomic number 9. So 1, 2, 3, 4, 5, 6, 7, 8, and 9. On fluorine, we're going to see that there's an electron that is unpaired, and that's going to tell us a lot about reactivity. Electrons, to be stable, they like to be paired. When you have elements that shows electron by themselves, that's going to make them more reactive. So this form of drawing the electron distribution by doing the orbital electron diagram allows us to see something about the reactivity of the element. Fluorine is one of the most reactive elements in the whole periodic table. So go ahead and practice that. You got these 4 elements. So make sure that you can fill up the diagram. Try to notice which one are going to end up with unpaired and paired electrons, and see if you can relate the diagram to the position on the periodic table by determining the period based on the highest number and the location on the S, P, D, or F block based on the highest orbital that you fill up, or the last orbital that you fill up. And with that said, we have enough practice now to write electron configuration and do the orbital diagram for atoms. And we're going to see all the information that we're going to be able to get out of that very soon. So when we come back, we are going to be identifying what the valence electrons are and what the core electrons are. And we're going to find an even easier way to write the electron configuration by just looking at the periodic table. So we have been doing it the hard way so we can lead to the easiest way, but understanding why we're doing it like that. So until the next time, I will see you soon. Take care.